How many seconds are left? 364 kilo electron volts. You need to select the type of isotope you are working with, which is iodine, at the new energy level. For each isotope you inject into the machine, you adjust your pulse height analyzer to your energy level. God bless it, that's right. I forgot, where were we? Oh, I wanted to show you the JASAC Phantom. Well, the JASAC Phantom is present in the image shown. This is called the JASAC Phantom. It is divided by something called SPECT. This is the view you see. This is a phantom. The term phantom refers to the phantoms you have seen, like the one used in the city, which is made of a material called perspex. Inside it, we place distilled water, and there is a specific design whose purpose is to test my machine. For example, we used to use a regular water phantom, which only contains water, but now we want to test a range of things. So, what do we test? I test the resolution, the uniformity, and the contrast of my system. I don't use the JASAC Phantom when testing my machine. I test my machine in what they call SPECT, meaning SPECT uniformity, and SPECT sphere. What does that mean? What do SPECT uniformity and SPECT sphere mean? When I place this phantom, I want to test it, and I need a set of cross-sections. I want to take images, and let's go back to the image we were working on. Save this image. This image is a cross-section. I obtain this cross-section just like you take a helical scan and get a scout image. The scout image for us is considered as if you are taking a picture like you see in an interior or posterior view, similar to an X-ray image, right? It's a two-dimensional image, correct? So you are not taking a cross-section, you are not getting a section, right? In the X-ray or the scout image or the scanogram, the image of the JASAC Phantom that I obtained, doctors, is an image where I captured the phantom I showed you, but I captured it in something called SPECT, not planar. There are two types of imaging. One is called planar imaging, and the other is called SPECT imaging. Planar imaging is like the image you take for an X-ray. Interior, posterior, lateral, or whatever. The image shows a superimposed component on some organs. It takes a planar image, so I call it planar imaging. It creates a cross-section that cuts through the JASAC Phantom, and this is what I am doing in this phantom. The black point you see is what I call roots. Why is it black? Because it has no radioactivity. It has no radioactive material. The white part is an inverted image. This is my radioactive material. I fill the JASAC Phantom with distilled water, and then add radioactive material using a specific technique in a certain way. After that, I started imaging. When I had a very large window, the resolution here was very low, and your contrast was poor. However, when your window was small, the resolution improved. I use this test or this examination to test SPECT resolution, SPECT uniformity, or SPECT contrast, as we will see, or SPECT uniformity, or SPECT contrast, as we will see in After we talk about the different types of imaging techniques and their applications in various fields and their significance in modern medicine, we will then proceed to discuss this particular test in detail and how it is conducted step by step in a comprehensive manner, ensuring that each step is clearly understood. So far, everything is clear, right? No problems? Very good then. Let's go back to a slightly complicated point. There is a man named Fourier. He is a very great mathematician. He said that everything exists. And if you have an object, this object exists in a certain place. And you can express that it is present in that specific place using something called the special domain, which is spatial. So, do you remember the power phantom or the line pairs that we talked about in the previous lectures? And of course, you remember the MTF, modulation transfer function. The signal that comes to you, or the signals that come to you for imaging, arrives with a certain frequency and a certain amplitude, which expresses the intensity of the signal. This means that the content is indeed high, with a very high intensity, and the frequency represents the objects present or the size of those objects. What does this mean? For example, if you remember from the line pairs lectures, we used to say that if I have a line pair in this shape, line pairs mean that there is a line and next to it there is a space. For example, this line could be made of lead or a high density material, and next to it there is a gap. Then there is another line next to another gap. When these distances are large enough, your eye can distinguish that these are lines. I call each line next to a gap a line pair. Each line next to a gap is called a line pair. If the distances or gypsum are significantly reduced, the number of line pairs per centimeter increases. Again, if I have line, assuming this is a centimeter, how many line pairs do I have per centimeter? Three line pairs per cm. Let's assume in this same cm I placed 1, 2, 3, 4, 5. So I have 5 line pairs per cm. Now, these 3 line pairs per cm represent my object. You can express it in the frequency domain. What does frequency domain mean? It means the object itself gives you a line, and next to it a gap, and then a line and a gap. So there is a frequency, a repetition of the lines that exist, right? If we say that this line will give you a high signal or a high peak, for example, or let's say that the gap will give you a high peak and the line will give you a low peak, what can I do? I can create a curve like this. All right, here we have how many cycles? In 2 cycles. This is the peak and this is the peak. You can recognize this as the peak, 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 peak. How many peaks? 1, 2, 3, 4. So, which one of them has the highest frequency? How many Lindberghs? Yes. So, when I mentioned the gaps and the graphical distances between the devices that I have, the team is very high. So here is the same idea. These devices and the Lindberghs I have, the graphical distances here were large, then they decreased and became very small, so your frequency increases. But take note, when the frequencies were here a little in this area or in this area, I was able to achieve high contrast. I was able to see better and clarify better, okay? So, the value of the MTF, which is the modulation transfer function that we were talking about earlier. Do all the doctors with us know about the topic of the modulation transfer function, MTF, or not? Oh, right. In the part about low frequency, you find a high value here, 100%. Then, when you move to high frequency, you see that your modulation transfer function, MTF, is decreasing. The same idea applies here if you have objects A, B, C, and D present inside this patient. For example, this device has a high count, but its size is large. This one is bigger, but its count is low. The count rate is low, so the amplitude here is low as well. The signal itself, as long as the count is low within the patient, the amplitude itself will be low. All right. And if its size is large, you will find that your peak is broad in this way. Okay, the same idea here. The size is smaller, but the count is high, so the amplitude is higher. Because the size is smaller, the broadening of the peak decreases. Here, it's low, and the size is smaller. A smaller size means the width decreases, and the peak is lower because the count is lower. Here, the count is higher in D, but the size is smaller, so this broadening is less. Each object has a specific size, and the machine's ability to see very small objects reflects its resolution. You can determine how large an object is based on this. Of course, nuclear imaging is considered the worst imaging modality in terms of resolution. It is indeed the worst in this regard, right? Well, it tells you about the transformation from what is called the special domain to the frequency domain. What does this is called the Fourier transformation. This is through mathematics or through a specific equation that I will enter. But what I want to understand is when you read the term special domain and frequency domain. So you have expressed these things inside the patient in a way that is described by frequency. It has amplitude. Just tell me, is there a specific team inside the bush? The signal that comes to you is that if I have an object like this object contains radioactive material and emits a signal. Here, there is a part that I call the background. The background always gives you low frequency. So you will find that its frequency is always low. The object with the highest activity falls in between low frequency and high frequency. So what does high frequency represent? What comes to you in high frequency? The noise. There is noise. I have 3 areas in the skin body, or 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 3 areas in the skin body. All right? The object itself, which has high activity, has a slightly higher frequency. However, because your object size is large, or the organ containing the radioactive material gives you a strong signal, you can differentiate it as a special location compared to the other organs. So when you translate from special to frequency, it gives you a low frequency. And forget it, it is indeed low. It's not very large. The significant noise present in the image represents the extremely small and intricate objects that you cannot detect, and therefore causing significant distortion in the overall image quality. Additionally, you have 3 distinctly separate regions, namely the background, the object information, and the noise area. Right now, when I receive this signal and want to process the image itself, we have, for example, in the city, the ability to use a filter that can perform smoothing or sharpening on the image. When you apply smoothing to the image or use a specific filter, the image becomes smoother and the noise decreases. When you sharpen the image, it becomes sharper and the noise decreases a little, right? Is that clear, doctors? The same idea applies in nuclear imaging. The signal you receive can be processed using a set of filters to remove the existing noise. How do I remove the noise? There are 2 or 3 types of filters. There is something called a low-pass filter, a high-pass filter, and a band-pass filter. The low-pass filter allows low frequencies to pass through, while the high-pass filter allows high frequencies to pass through. The high-pass filter refers to high frequency, while the band-pass filter covers a specific range of frequencies, right? The low-pass filter primarily allows low frequencies to pass through, slightly extending into the medium frequency range, while completely removing high frequencies from your signal, thus eliminating high noise. The high-pass filter works by creating a curve that captures the object part and also takes some noise from the image. The band-pass filter captures a specific area. These filters are essentially based on mathematical equations designed to process incoming signals and remove certain frequencies. There are various types of filters available, such as the Butterworth filter, which is one of the most well-known filters in nuclear imaging. The filter, as we mentioned, has a low-pass filter, a high-pass filter, and a band-pass filter. Among the filters we use, the Butterworth filter is considered a low-pass filter. Now pay attention, I was saying that my frequency will be given in cycles per second, cycles per pixel. Why? Because the topic of resolution or the signal comes from where and is stored where? In the pixel. Remember the topic of pixel size and how it relates to resolution. If your pixel size is small, does the resolution increase or decrease? What does the entire resolution depend on? If your field of view is large, the pixel size for the same matrix will increase, which will reduce the resolution because of the pixel size. It is about the field of view, which is the area you can see or the area you are capturing. What are its dimensions? It relates to the matrix size, which indicates how many rows and columns, how many squares are present within the field of view. For example, when you take a picture with your mobile camera and step back a bit, you expand the field of view that you can see, enlarging the area that the camera can capture. So, you have increased your field of view. But the image that will come out will have the same matrix, the same dimensions, the same squares. So each square's size will increase to cover your entire field of view. If you have 100 squares and you set your field of view to 10 centimeters, and then you increase your field of view to 100 centimeters, then the square must increase in size so that the 100 pixel squares inside the image cover those 100 centimeters in the field of view. This means that the pixel size will decrease. So when the pixel size decreases, why does the resolution increase? Because as we discussed earlier, if I have an object that is small and my pixel size is large this way, and there are 2 objects that are close together, they will give you the same signal. So, if you took these signals and recorded them in a large pixel, can you doctors distinguish whether this signal is coming from this object or that object? You won't be able to. Therefore, the pixel size must be small, so we need to divide this large size into smaller parts to differentiate each pixel and distinguish the 2 signals coming in. Thus, increasing the matrix size increases the resolution. Why? Because when you increase the matrix size, you increase the number of pixels within the same field of view, which is still 100 centimeters. You have increased the number of pixels present, so each pixel size decreases, enhancing the resolution and allowing you to see finer details. But this comes at the expense of noise. The noise will increase. Why are you commenting? Because you started to reach very high frequencies within the image that you don't need. You started to make it look like you are giving a sharp image in the city, and you see it as sharp, but you find the image starting to become noisy because there are high frequencies that began to appear from the small objects present in your image. So, the high noise is there. What do you do to overcome the noise? With the matrix size, if we are talking about the city, and we are talking about X-ray, increase the milliampere, increase your parameters. Why? Because you will provide a high number of photons that can be stored in the counts, which gives you smoothing in the image. As for nuclear imaging, increase the examination time, give the patient a higher dose to increase the high counts that will be received and recorded in the pixel. Because when you reduce the pixel size, each pixel here, instead of receiving two signals together, averages them and becomes a smooth image. You keep each pixel small and reach half the number that was received when it was larger. Increasing the resolution is important, but you needed to provide a diagnostic image for you. So this is a drawback of increasing the matrix size. What is its relation to the resolution of the image? The filter plays a very important role in helping you. Which filter? Doctors, didn't you explain this? Doctor, is this filter the same as the one you mentioned? As you said, this is from the filter load, so it will allow low energy force to pass through. The low energy will not pass. No, Dr. Hani, there is a difference between energy and frequency. The low frequency will pass. What is low frequency, Dr. Hani? What is low frequency again? Doctor, there is a difference between them. What is low frequency like Dr. Hani? The low frequency, look, in this case, sorry, if it was from you, its purpose is not what I'm saying because the low frequency object is large and there is high radioactive material. All right, there is a big difference between it and the background, and there is a large distance between it and the background. There is another object here. These two are illuminated, all right? So here you have a mid signal. And what is the mid signal? Well, if you have a very small field and there is another very small field next to it, this translates to high frequency like this shape. I want to move together. I want to enchant you a little. I want to ask you to move a bit. When patients come to me and inject radioactive material, the radioactive material is supposed to target what? It targets argon, right? For me, the argon, where the radioactive material has gone, will be very bright. Will it be bright for me or not? I should have done something targeted for it to be bright, right? So, naturally, what is the relationship of this bright argon to the background? Keep in mind that inside the patient's body, it is itself bright and the background is completely off, right? And it itself, in terms of size, is my target. I want to go see it. I want to receive its signal. The signal that I got from it. Just keep in mind the signal that I got from it. What is the object that is illuminated for me in relation to the background or any other object? Is that clear? The signal. Forget about the amplitude part. The amplitude is a different story, but I'm talking about frequency. What does frequency mean? Can I see this illuminated object in relation to the background or not? Will I be able to see it correctly? Why? Because it is taking a signal from the radioactive material. As long as you can see the object in relation to the background around it, what does that mean? It means that your frequency is low. What does low frequency also mean? Simply put, if I have an object that is small in size next to another small object. Okay? Now I call this a special domain, meaning both objects are within the patient's view. This is a special domain, right? Now, do you see these two inside the patient's body? Okay, for you, is the separation between them large or small? Small. So, if it is small, let's assume there are several other objects next to them of the same size and the same distance between them. What will they do together? They will create a signal that undergoes repetition or is reiterated. So, at this distance, is it with a high frequency or a low frequency? With a high frequency. Why? Because your object size is small and the gap between your object and the adjacent object is small. In contrast, the origin of interest that I want to image has high activity and its size is considered large in comparison.